Climate Systems Explained, Earth's Delicate Balance. Part 1, Introduction, Why Climate Matters. From space, Earth looks calm. A blue and white world, balanced and alive. But beneath this peaceful image, powerful forces are constantly at work. Hurricanes grow stronger. Heat waves last longer. Ice that once took thousands of years to form is disappearing within decades. These changes are not random. They are signals. Earth is governed by systems, vast, invisible processes that regulate temperature, move energy, and sustain life. Together, they form what we call the climate system. But what happens when this delicate balance is pushed too far? To understand what is happening to our planet today, we must first understand how Earth regulates itself. Climate is often confused with weather, but they are not the same. Weather is short-term, today's rain, tomorrow's sunshine. Climate is long-term, patterns measured over decades, even centuries. Climate determines where forests grow, where oceans circulate warmth, and where civilizations rise and fall. For thousands of years, human society has depended on a stable climate, one that no longer behaves as it once did. In this documentary, we will explore Earth's climate systems. The atmosphere above us. The oceans below us. The gases that trap heat. And the role humanity now plays in reshaping them. Because understanding how the system works is the first step toward understanding what comes next. What is climate? Climate is not a single event. It is not one storm, one heat wave, or one cold winter. Climate is the long-term pattern of temperature, rainfall, winds, and seasons, measured not in days, but over decades and centuries. At its core, climate is the result of a complex system. A global machine made up of many moving parts, all working together. Scientists call this the climate system. The climate system includes the atmosphere, the thin layer of gases surrounding our planet that controls temperature and weather. It includes the oceans, which absorb vast amounts of heat and slowly move it around the globe through powerful currents. It includes the land, shaping wind patterns, storing heat, and supporting ecosystems that regulate carbon. It includes ice glaciers, ice sheets, and sea ice that reflect sunlight and help keep Earth cool. And it includes life itself. Plants, forests, and microscopic ocean organisms quietly control how much carbon remains in the air. None of these parts work alone. Each one influences the others, constantly exchanging energy, water, and gases. The atmosphere warms the ocean. The ocean reshapes the atmosphere. Ice reflects sunlight. Life alters the chemistry of the air. Climate is not controlled by one force, but by the balance between many. For most of human history, this system remained remarkably stable. Stable enough for agriculture. Stable enough for cities. Stable enough for civilizations to flourish. But when even one part of this system changes too quickly, the effects ripple outward, across continents, oceans, and generations. To understand how Earth's climate truly works, we must begin where most of its heat is stored. In the oceans. Why this topic matters today? Today, the climate system is changing faster than at any point in recorded human history. Global temperatures are increasing. Heat waves are becoming longer and more intense. Storms are carrying more energy. Rainfall is falling where it once did not, and failing where it once sustained life. These are not isolated events. They are connected symptoms of a system under strain. Human civilization did not emerge at random. It developed during a rare period of climate stability. A time when seasons were predictable, rainfall followed patterns, and coastlines changed slowly. Farming, trade, cities, and global societies all depend on climate patterns that remain within narrow limits. When those limits shift, the consequences ripple far beyond the environment. Infrastructure is stressed. Food systems are disrupted. Water becomes uncertain. Entire regions face risks they were never designed to handle. Climate change is not only an environmental issue. It is a challenge to economics, security, health, and long-term stability. Understanding what is happening requires more than headlines or single statistics. It requires understanding the system itself. In this documentary, we will explore how Earth's climate works. From the atmosphere above us, to the oceans that store and move heat, to the greenhouse gases that regulate temperature. We will examine how human actions are altering these systems, and what the science reveals about possible futures. Climate is not just about the planet. It is about the conditions that allow human life to thrive. To understand where we are going, we must first understand how the system works. Part 2: Earth's climate systems. The atmosphere. Surrounding our planet is a layer so thin it would nearly vanish if Earth were the size of an apple. And yet, this fragile shell makes life possible. This is the atmosphere, a mixture of gases held in place by gravity, constantly moving, mixing, and interacting with the surface below. Layers of the atmosphere. The atmosphere is divided into layers, each with a distinct role. Closest to the surface is the troposphere. This is where weather happens, where clouds form, winds blow, and almost all human activity takes place. Temperatures here generally decrease with altitude, allowing warm air to rise and cool air to sink, driving weather patterns across the globe. Above it lies the stratosphere, a calmer region where temperatures increase with height. This layer contains the ozone layer, which absorbs much of the sun's harmful ultraviolet radiation, protecting life on Earth. Beyond these lie thinner, less familiar layers, but the troposphere and stratosphere do most of the work when it comes to climate. Role of atmospheric gases. The atmosphere is made mostly of nitrogen and oxygen. But it is the trace gases, present in much smaller amounts, that play an outsized role in regulating temperature. Certain gases allow sunlight to pass through the atmosphere, warming Earth's surface, but slow the escape of heat back into space. This process is known as the greenhouse effect, a natural mechanism that keeps our planet warm enough for liquid water and life. Without it, Earth would be a frozen world. Sunlight in, heat out. Climate begins with the sun. Energy arrives as sunlight, passing through the atmosphere and reaching land and oceans. The surface absorbs this energy and warms up. That heat is then released back towards space as infrared radiation. Some of this heat escapes freely. Some is absorbed and re-emitted by atmospheric gases, slowing its journey outward. The balance between incoming sunlight and outgoing heat determines Earth's average temperature. when this balance shifts. When more energy stays in the system than leaves it. The planet warms. Small changes in atmospheric composition can therefore lead to large changes in climate. But the atmosphere does not act alone. Most of the excess heat it traps does not remain in the air. It is absorbed by the vast body covering more than 70% of our planet. The oceans. The hydrosphere. Beneath the atmosphere lies the largest and most powerful component of Earth's climate system. Water. Covering more than 70% of the planet, Earth's oceans are not just bodies of water. They are vast reservoirs of heat, absorbing, storing, and redistributing energy around the globe. Oceans as heat reservoirs. Water has a unique ability. It can absorb enormous amounts of heat without rapidly increasing in temperature. This property allows the oceans to act as a thermal buffer, slowing down temperature changes that would otherwise be extreme. More than 90% of the excess heat trapped by greenhouse gases ends up in the oceans. Without the oceans, Earth's atmosphere would warm far more quickly and far more violently. But oceans do not simply store heat. They move it. Warm water flows from the equator toward the poles. Cold water sinks and returns toward the tropics. In doing so, oceans help regulate climate across continents, moderating winters, cooling summers, and shaping rainfall patterns. The water cycle. Heat absorbed by the oceans does something else. It drives the water cycle. As the sun warms the surface, water evaporates, rising into the atmosphere as invisible vapor. Higher up, cooler temperatures cause this vapor to condense into tiny droplets and ice crystals, forming clouds. Eventually, gravity pulls this water back to the surface as precipitation, rain, snow, or ice. This continuous cycle transfers heat, shapes weather, and connects oceans, land, and atmosphere into a single system. Clouds as climate regulators. Clouds play a unique and complex role in climate. On one hand, bright clouds reflect sunlight back into space, cooling the planet. On the other, clouds also trap heat near the surface, especially at night, acting like a blanket. Whether clouds cool or warm the planet depends on their type, altitude, thickness, and location. Low, thick clouds tend to cool. High, thin clouds often contribute to warming. Small changes in cloud cover can therefore have large effects on global temperatures. This makes clouds one of the most important and least understood elements of the climate system. Together, the oceans, the water cycle, and clouds act as Earth's temperature stabilizers. But this balance depends on slow, steady movement. And when that movement changes, the effects are felt across the entire planet. To understand how heat truly travels around Earth, we must now follow the currents beneath the surface. The great circulatory system of the oceans. The cryosphere and biosphere. At Earth's extremes, where temperatures are lowest, another powerful regulator comes into play. Ice. The cryosphere, Earth's frozen shield. The cryosphere includes ice caps, glaciers, sea ice, and frozen ground. Though it covers a smaller area than the oceans or atmosphere, its influence on climate is immense. Glaciers act as long-term freshwater storage. Ice sheets help stabilize sea levels. Sea ice forms a seasonal lid over polar oceans, insulating water below and shaping global circulation. But ice does something even more important: the albedo effect. Ice is bright. When sunlight hits it, much of that energy is reflected back into space. This reflectivity is called albedo, and it is one of Earth's most effective cooling mechanisms. Dark surfaces like open water or land absorb more heat. Bright surfaces like ice reflect it. When ice melts, Earth absorbs more energy. More absorption leads to more warming. More warming leads to more melting. This feedback loop can accelerate climate change far beyond the initial trigger. The biosphere, life is a climate regulator. Alongside ice, life itself plays a central role in regulating climate. Through photosynthesis, plants draw carbon dioxide from the atmosphere and store it as biomass in trunks, leaves, roots, and soils. Forests act as vast carbon reservoirs. Grasslands stabilize soils. Wetlands store carbon for centuries beneath waterlogged ground. Plankton and the ocean carbon pump. Even more influential, though largely invisible, are microscopic ocean organisms known as plankton. These tiny life forms absorb carbon dioxide near the ocean's surface. When they die, some of that carbon sinks into the deep ocean, effectively locking it away for hundreds or even thousands of years. This process, known as the biological carbon pump, helps keep atmospheric carbon levels in balance. Interconnected systems. Ice regulates how much sunlight Earth absorbs. Life regulates how much carbon remains in the air. Together, the cryosphere and biosphere act as stabilizers, slowing change, buffering extremes, and maintaining balance. But these systems are sensitive. When temperatures rise too quickly, ice retreats. Ecosystems weaken. Feedbacks begin to reinforce one another. As ice melts, fresh water flows into the seas, altering density, circulation, and the movement of heat itself. To understand what happens next, we must follow that heat through the vast, moving pathways of the oceans, the currents that power Earth's climate engine. Part 3: Ocean Currents, Earth's Heat Engine. Why oceans control climate? To understand Earth's climate, we must look beyond the sky to the vast, moving body that quietly governs temperature across the planet. The oceans. Oceans, the planet's primary heat sink. When greenhouse gases trap extra heat in the climate system, most of that energy does not remain in the atmosphere. More than 90% of the excess heat generated by human activity is absorbed by the oceans. This single fact explains why the oceans exert such powerful control over Earth's climate. Water warms slowly and cools slowly. This allows the oceans to absorb enormous amounts of heat without dramatic temperature spikes. In effect, the oceans act as a thermal shock absorber, protecting the atmosphere from rapid and extreme warming. Heat storage versus heat transport. But absorbing heat is only part of the story. Oceans do not simply store energy, they move it. Heat absorbed near the equator does not stay there. It is transported across thousands of kilometers by ocean currents. Warm water travels toward higher latitudes, releasing heat into the atmosphere. This process moderates climates far from the tropics. making some regions warmer and wetter than they would otherwise be. Without this redistribution, Earth's climate would be far more extreme, with hotter tropics and much colder poles. The ocean-atmosphere connection. The oceans and atmosphere are locked in constant exchange. Heat stored in the ocean fuels evaporation, transferring energy into the atmosphere in the form of water vapor. This energy drives winds, clouds, and storms, shaping weather systems around the globe. At the same time, winds at the surface push the ocean itself, generating currents that move heat back through the system. It is a two-way relationship. The atmosphere shapes the oceans. The oceans shape the atmosphere. Together, they form a single, interconnected engine. One that regulates temperature, rainfall, and climate stability on a planetary scale. When this engine runs smoothly, climates remain relatively stable. But when ocean heat storage or heat transport changes, the effects are felt everywhere. To see how this engine truly works, we must follow the currents themselves. From winds at the surface to the slow, deep circulation of the global ocean. This is where Earth's heat begins its long journey. Surface ocean currents. Not all ocean movement happens in the deep. At the surface, a vast network of currents is driven by the winds that circle our planet. Wind-driven motion. As sunlight heats Earth unevenly, it creates pressure differences in the atmosphere. These differences generate winds, steady, powerful flows of air that sweep across the oceans. When wind blows over water, it transfers energy through friction, pulling the ocean's surface along with it. Over time, this motion organizes itself into large-scale currents that span entire ocean basins. The role of Earth's rotation. Earth's rotation adds a crucial twist. As moving water travels across the planet, it is deflected, curving to the right in the northern hemisphere, and to the left in the southern hemisphere. This deflection shapes surface currents into enormous circular systems known as gyres. Major surface current systems. Near the equator, intense sunlight heats surface waters. Trade winds push these warm waters westward, creating strong equatorial currents that transport heat across the tropics. This movement concentrates warm water in certain regions, influencing rainfall patterns and storm formation. From the tropics, warm currents flow toward higher latitudes along the edges of continents. As they move poleward, these currents release heat into the atmosphere. This transfer of heat can dramatically warm nearby land, softening winters and increasing moisture in the air. Meanwhile, cold currents flow from polar regions toward the equator. These currents cool the air above them, often leading to drier climates along nearby coastlines. Together, warm and cold currents form a global conveyor of surface heat. Influence on regional climates. Surface currents help explain why regions at the same latitude can experience very different climates. Coastal areas influenced by warm currents tend to be milder and wetter. Regions influenced by cold currents are often cooler and drier, sometimes even desert-like, despite being near the ocean. These currents shape storm tracks, rainfall zones, and seasonal patterns. Warm surface waters fuel tropical storms, providing the energy they need to grow. Cooler waters, by contrast, limit storm strength. A delicate balance. Surface currents respond quickly to changes in wind patterns. When winds shift, due to natural cycles or a warming climate, surface currents shift as well. These changes can alter rainfall, intensify droughts, or increase flooding. Sometimes thousands of kilometers away from where the change began. But surface currents are only the visible half of Earth's ocean circulation. Beneath them lies a slower, deeper system, driven not by wind, but by differences in temperature and salt. A circulation that connects all the oceans of the world. Deep ocean circulation. Beneath the winds and waves lies a circulation system far larger and far slower than anything at the surface. A global movement of water that connects every ocean on Earth. The global conveyor belt. Scientists call this system thermohaline circulation, a name that comes from two words. Thermo, meaning heat, and haline, meaning salt. Simply put, this circulation is driven by differences in temperature and salinity. How temperature and salinity move the oceans. Cold water is denser than warm water. Salty water is denser than fresh water. When ocean water becomes cold and salty enough, it sinks. This sinking motion pulls surface water down into the depths, setting massive currents in motion. In a few key regions, particularly near the polar oceans, surface water cools dramatically. As sea ice forms, salt is pushed into the surrounding water, increasing its density. The result is heavy, cold, salty water that sinks to the ocean floor. A slow but powerful system. Once it sinks, this dense water begins a long journey, flowing slowly through the deep ocean. It may take hundreds, or even thousands of years, for a single parcel of water to complete this global circuit. Though slow, this circulation moves enormous amounts of heat and carbon, quietly stabilizing Earth's climate over long time scales. Why deep circulation matters. Deep ocean circulation helps regulate how heat is stored and released. It ventilates the deep ocean, allowing oxygen to reach the depths, and carbon to be stored far from the atmosphere. It also supports marine ecosystems and influences surface climates far away. What happens if the system weakens? This system depends on density differences remaining strong. But as the planet warms, melting ice adds fresh water to the oceans, reducing salinity. Fresher water is lighter. It resists sinking. If sinking slows, the entire circulation weakens. A weakened deep circulation means less heat transported to certain regions. Some areas may cool, even as the planet warms overall. Rainfall patterns could shift. Marine ecosystems could be disrupted. Heat could build up in unexpected places. A tipping system. Thermohaline circulation is resilient, but not limitless. Push it too far, and it may not respond gradually. It may change abruptly. The oceans do more than store heat. They move it, lock it away, and release it, shaping climate across centuries. But oceans are only part of the story. Above them, invisible gases determine how much heat enters the system in the first place. To understand that control, we must now turn to the atmosphere once again, and the gases that trap heat around our world. Part 4. Greenhouse gases, the heat trap. The greenhouse effect. Every moment of every day, Earth receives energy from the sun. This energy arrives as sunlight, passing through space, through the atmosphere, and down to the surface below. How Earth stays warm naturally. When sunlight reaches Earth's surface, some of it is reflected back into space. But much of it is absorbed by land and oceans, warming the planet. That warmth does not stay forever. Earth releases energy back towards space as infrared heat. If all of that heat escaped freely, our planet would be cold and lifeless. The atmospheric blanket. Instead, a small group of gases in the atmosphere slows the escape of heat. These gases act like a blanket, not trapping heat completely, but holding enough of it to keep Earth warm. This process is known as the greenhouse effect. It is a natural and essential feature of Earth's climate system. Why the greenhouse effect is essential for life. Without the greenhouse effect, Earth's average surface temperature would be far below freezing. Liquid water would be rare. Ecosystems as we know them could not exist. The greenhouse effect keeps temperatures within a range where water remains liquid. Chemistry can function, and life can thrive. In this sense, the greenhouse effect is not the problem. Natural versus enhanced greenhouse effect. For thousands of years, this natural process remained in balance. Heat entered the system. Heat left the system. Temperatures stayed within a relatively narrow range. But when the concentration of greenhouse gases increases, the blanket becomes thicker. More heat remains in the system than escapes. This is known as the enhanced greenhouse effect. The difference between natural and enhanced warming is not the process itself, but the amount. A thicker blanket does not create heat. It slows its escape. Setting the stage. Understanding this distinction is critical, because the question facing the modern world is not whether the greenhouse effect exists, but how much it has been strengthened, how quickly it is changing, and what that means for the climate systems we have explored. To answer that, we must look more closely at the gases themselves, where they come from, how they behave, and how long they remain in the atmosphere. These are the gases that control Earth's thermostat. Major greenhouse gases. Not all greenhouse gases behave the same way. Some remain in the atmosphere for centuries. Others disappear more quickly, but trap far more heat while they are present. Understanding these differences is key to understanding climate change. Carbon dioxide. Carbon dioxide, or CO2, is the most influential greenhouse gas produced by human activity. It is released when fossil fuels are burned, forests are cleared, and cement is produced. What makes carbon dioxide unique is its longevity. Once released, a portion of CO2 remains in the atmosphere for hundreds of years. This means today's emissions will influence climate for generations to come. Methane. Methane is far less abundant than carbon dioxide, but far more powerful. Molecule for molecule, Methane traps many times more heat than CO2. It is released from natural wetlands, livestock digestion, rice farming, landfills, and fossil fuel extraction. Methane's strength lies in its intensity. It remains in the atmosphere for only about a decade. But during that time, its warming impact is extremely strong. Nitrous oxide. Nitrous oxide is less well known, but highly potent. It is released primarily through agricultural activities, especially the use of nitrogen-based fertilizers. Nitrous oxide persists in the atmosphere for over a century. And on a per-molecule basis, it traps far more heat than carbon dioxide. Water vapor. Water vapor is the most abundant greenhouse gas in the atmosphere. But unlike the others, it behaves differently. Water vapor responds to warming rather than directly causing it. As temperatures rise, more water evaporates. More vapor then traps additional heat. This creates a feedback loop, amplifying warming already underway. Lifespans and warming power. The impact of a greenhouse gas depends on two key factors: how strongly it traps heat, and how long it remains in the atmosphere. Carbon dioxide is weaker per molecule, but long-lived. Methane is powerful, but short-lived. Nitrous oxide is both potent and persistent. Water vapor amplifies whatever warming already exists. Together, these gases determine how thick Earth's atmospheric blanket becomes. And as their concentrations rise, so does the amount of heat retained within the climate system. But greenhouse gases do not act in isolation. Their effects trigger responses throughout the climate system, from melting ice to warming oceans. These responses can reinforce warming in powerful ways. They are known as feedback loops. Feedback loops. Climate change is not driven by a single cause acting alone. It is shaped by processes that respond to warming and then amplify it. These processes are known as feedback loops. What is a feedback loop? A feedback loop occurs when a change in the climate system triggers effects that either reinforce or reduce that original change. Some feedbacks slow warming. Others accelerate it. The most concerning feedbacks are those that reinforce warming, pushing the system further in the same direction. Melting ice and the albedo feedback. Ice reflects sunlight. This reflectivity helps keep Earth cool. But as temperatures rise, ice melts, exposing darker ocean water or land beneath. Dark surfaces absorb more sunlight than ice. This extra absorption increases warming, which leads to more melting. This is known as the ice albedo feedback, a self-reinforcing cycle that accelerates temperature rise, especially in polar regions. Warming oceans and carbon absorption. Oceans play a crucial role in absorbing carbon dioxide from the atmosphere. Cooler water can absorb more CO2. As oceans warm, their ability to absorb carbon decreases. Less carbon is taken out of the atmosphere. More carbon remains aloft, strengthening the greenhouse effect. This feedback does not cause warming on its own, but it reduces one of Earth's natural defenses against it: permafrost thaw and methane release. In the far north, vast areas of soil remain frozen year-round. This frozen ground is called permafrost. Permafrost stores enormous amounts of organic carbon, material that has been frozen for thousands of years. As temperatures rise, permafrost begins to thaw. Microbes break down the once frozen material, releasing greenhouse gases into the atmosphere. One of these gases is methane, a powerful heat-trapping gas. This creates another feedback loop. Warming leads to thawing. Thawing leads to gas release. And gas release leads to more warming. Why feedback loops matter? Feedback loops help explain why climate change can accelerate over time. They link ice, oceans, land, and atmosphere into a tightly connected system. Changes in one part of the system rarely stay isolated. Feedbacks do not mean the climate system is unstable by default. But they do mean that speed matters. Slow changes allow systems to adjust. Rapid changes can overwhelm natural balancing processes. Understanding feedback loops helps scientists identify potential tipping points, thresholds beyond which change becomes harder to reverse. And it reminds us that the climate system responds not only to what we emit, but to how the planet itself reacts. In the next part of this documentary, we will examine the role of human activity more directly, and how modern society has altered Earth's natural balance. Because the climate system does not only respond to nature, it responds to us. Part 5: Human impact on the climate system. Industrialization and emissions. For most of Earth's history, the climate system changed slowly. Shaped by volcanic activity, orbital cycles, and natural feedbacks. That pace changed dramatically with the rise of industrial society. The turning point: fossil fuels. Beginning in the industrial era, humans learned to unlock vast amounts of energy stored underground. Coal, oil, and natural gas, formed over millions of years, were burned in a matter of centuries. This process released carbon that had long been locked away. Energy, transportation, and industry. Fossil fuels became the backbone of modern energy systems. They power electricity generation, fuel transportation across land, sea, and air, and drive industrial processes that produce steel, cement, and chemicals. These activities transformed living standards, economies, and global connectivity. They also transformed the composition of the atmosphere. Carbon dioxide and the carbon cycle. Under natural conditions, carbon moves slowly between the atmosphere, oceans, land, and living organisms. Plants absorb carbon. Oceans store it. Geological processes lock it away over long timescales. For thousands of years, this cycle remained in approximate balance. Industrial emissions introduced a new factor: carbon entering the atmosphere far faster than natural systems could absorb it. The result is a buildup of carbon dioxide in the air. This buildup strengthens the greenhouse effect, not by creating heat, but by slowing its escape, disrupting a long-standing balance. The climate system is resilient, but it has limits. When carbon enters the atmosphere faster than forests and oceans can remove it, balance gives way to accumulation. And accumulation leads to warming. Because greenhouse gases mix evenly in the atmosphere. Emissions released in one region affect the entire planet. Climate change is therefore not local. It is global, setting the stage for broader impacts. Industrialization did not act alone. Changes in land use, agriculture, and resource extraction further altered the climate system, often reinforcing the effects of emissions. To understand the full picture, we must now look beyond smokestacks and engines to how humanity has reshaped the surface of the planet itself. Because altering the land also alters the climate. Land use changes. Human influence on the climate system is not limited to emissions from fuel and industry. It is also written across the surface of the planet itself. Deforestation. Forests play a critical role in regulating climate. They absorb carbon dioxide from the atmosphere and store it in living tissue and soils. When forests are cleared, whether for timber, agriculture, or development, this stored carbon is released back into the atmosphere. At the same time, the planet loses one of its most effective natural carbon sinks. The result is a double impact. More carbon released, and less capacity to remove it. Urban heat islands. Cities also alter local climate in powerful ways. Concrete, asphalt, and metal absorb and retain heat far more efficiently than vegetation. This creates urban heat islands, areas where temperatures can be several degrees higher than surrounding regions. Reduced vegetation means less cooling through evaporation. The added heat increases energy demand, stresses infrastructure, and can worsen heat-related health risks. Agriculture and livestock emissions. Agriculture is essential for human survival, but it also contributes to climate change in complex ways. Livestock such as cattle produce methane during digestion. Rice cultivation releases methane from flooded soils. Nitrogen-based fertilizers lead to emissions of nitrous oxide. These gases are released in smaller quantities than carbon dioxide, but they are far more effective at trapping heat. A transformed landscape. Over centuries, human land use has reshaped ecosystems across the globe. These changes influence how much sunlight is absorbed, how water moves through the system, and how carbon cycles between land and atmosphere. Climate change, in this sense, is not only about what we emit, but about how we manage the land beneath our feet. Many of these changes extend beyond the land itself. They affect rivers, coastlines, and ultimately the oceans, where much of the planet's excess heat and carbon ends up. To understand the full impact of human activity, we must now return to the oceans and examine how they are responding to a changing world. Oceans under stress. The oceans have absorbed the majority of the excess heat and carbon released by human activity. In doing so, they have protected the atmosphere from even faster warming. But this protection comes at a cost. Ocean warming. As greenhouse gases trap more heat, oceans steadily warm. This warming does not occur evenly. Surface waters heat first, while deeper layers warm more slowly, changing how heat and nutrients move through the ocean. Warmer water holds less oxygen. As oxygen levels drop, marine life faces increasing stress, particularly species adapted to narrow temperature ranges. Ocean acidification. Oceans also absorb a large portion of the carbon dioxide released into the atmosphere. When CO2 dissolves in seawater, it triggers chemical reactions that lower the ocean's pH. This process is known as ocean acidification. Acidification reduces the availability of carbonate ions, essential building blocks for shells and skeletons. Many marine organisms struggle to grow, survive, or reproduce under these conditions. Coral bleaching. Coral reefs are among the most sensitive ecosystems on Earth. Corals live in partnership with microscopic algae that provide them with energy and color. When water temperatures rise beyond a narrow threshold, corals expel these algae. The result is coral bleaching, a loss of color, energy, and resilience. If stressful conditions persist, corals can die. Ecosystem collapse. Coral reefs support an estimated quarter of all marine species. When reefs decline, entire ecosystems unravel. Fish populations fall. Coastal protection weakens. Food security and livelihoods are affected. Warming, acidification, and oxygen loss often act together, compounding stress on marine systems. A system under pressure. The oceans are resilient, but not infinite. Their ability to buffer climate change depends on limits that cannot be crossed indefinitely. As heat and carbon continue to accumulate, the risks to marine ecosystems grow. The state of the oceans offers a clear signal, not only of what has already changed, but of what may lie ahead. To understand where the climate system is heading next, we must step back and consider the broader consequences and the choices that still remain. Because the future of the climate system is not yet fixed. Part 6: Consequences and the Road Ahead. What the science shows. After decades of observation, measurement, and analysis, climate science now paints a consistent picture. The climate system is changing, and the evidence is visible across the planet. Rising sea levels. One of the clearest signals is rising sea level. As oceans warm, seawater expands. At the same time, melting glaciers and ice sheets add more water to the seas. Together, these processes are raising global sea levels, increasing the risk of flooding for coastal communities. Even small increases can turn rare floods into regular events. Stronger storms and heat waves. A warmer climate adds energy to the atmosphere. Warmer oceans fuel stronger storms, while warmer air holds more moisture, increasing the potential for intense rainfall. Heat waves are also becoming more frequent and severe. Extended periods of extreme heat place stress on ecosystems, infrastructure, and human health. Shifting weather patterns. Climate change does not affect all regions equally. Some areas experience heavier rainfall. Others face longer and more intense droughts. Seasonal patterns are shifting, altering growing seasons, water availability, and wildfire risk. Patterns, not isolated events. No single storm or heat wave can be attributed to climate change alone. But when trends repeat across continents and decades, the signal becomes clear. The climate system is moving away from the stable patterns that supported human societies for thousands of years. These changes represent the outcomes of processes we have explored. Heat trapped by greenhouse gases, stored and transported by oceans, amplified by feedbacks. The science shows what is happening. The question now is how the system responds in the decades ahead, and how human choices shape that response. Can the climate system recover? A question often asked is simple. Can the climate system recover? The answer depends on both nature's resilience and the pressure placed upon it. Natural resilience versus human pressure. Earth's climate system has changed before. Over millions of years, temperatures rose and fell. Ice advanced and retreated. Ecosystems adapted, migrated, or transformed. This history shows that the planet itself is resilient. But resilience has limits, especially when change happens rapidly. Today's warming is occurring far faster than most natural shifts of the past. And human activity continues to apply pressure faster than many systems can adjust. Timescales, decades versus centuries. Another key factor is time. Some parts of the climate system respond quickly. Atmospheric temperatures can stabilize within decades if greenhouse gas emissions are reduced. Other parts respond far more slowly. Oceans and ice sheets store heat over centuries. Changes already set in motion may continue long after emissions slow, shaping coastlines, ecosystems, and climate patterns for generations. The importance of tipping points. Not all change is gradual. Some systems can cross thresholds, known as tipping points. Beyond these points, change can accelerate rapidly or become difficult to reverse. Examples include large ice sheets, major ocean circulation patterns, and critical ecosystems. Avoiding these thresholds reduces long-term risk and preserves more options for recovery. A narrowing window. The climate system is neither fragile nor invincible. It can absorb change, but only up to a point. The choices made in the coming decades will influence whether change remains manageable or becomes self-reinforcing and persistent. Recovery, where possible, is measured not in years but in generations. And the direction the system takes depends on how closely human actions align with the limits of the planet itself. Closing message. Earth's climate is not controlled by a single force. It is shaped by connections. The atmosphere exchanges heat with the oceans. Ice reflects sunlight back into space. Forests and plankton quietly move carbon through air, land, and sea. Every part of the climate system influences the others, forming a balance that has allowed life to thrive for thousands of years. Human activity has become part of that system. The energy we use, the land we alter, and the gases we release now affect processes once shaped only by nature. This influence carries responsibility, not because the planet is fragile, but because the system responds to pressure. Climate change is not a distant or abstract concept. It is the result of how a global system reacts to what we do. And just as actions can disrupt balance, understanding can help restore it. The climate system will continue to change. That much is certain. What remains uncertain is how closely future change aligns with the limits of the planet and the needs of the societies that depend on it. Understanding the system does not provide simple answers, but it does provide clarity. Because understanding the system is the first step toward protecting it. If you found this documentary informative, consider supporting the channel. Like this video to help it reach more viewers. Share it with others who want to understand how our planet works. And subscribe for more in-depth educational documentaries like this one. Thank you for watching.